Hi, I Sasibhushan Tiwari welcome you all. In today's video, we will take up a problem from mechanics which is inspired from a rather tough problem asked in JEE Advanced few years back. I will leave it to your imagination to guess the year in which a similar problem was asked in JEE Advanced. Here is today's problem. A small sphere of mass small m, that is 1 gram, is constrained to move along a smooth horizontal floor between a fixed vertical wall and a rectangular block of mass capital M, that is 1 kilogram. Initially, the block is at a distance L0 from the wall. This distance is L0, and it is at rest. The block is at rest. The sphere is projected from the wall towards the block with an initial velocity of 10 meter per second. This is the small sphere which was projected towards the block at a speed of 10 meter per second. Assume all collisions are perfectly elastic and the speed of the block to remain much smaller than the sphere for the interval considered in this particular problem. Determine the speed of the sphere at the instant the distance between the wall and the block has doubled. What will be the speed of this small sphere by the time distance separation between the wall and the block has become 2L0? Calculate the ratio of average force exerted by the sphere on the fixed wall when the separation becomes 2L0 compared to the initial average force that was acting on the wall because of regular impact from the ball. Read the problem once and give it a try on your own. I am getting out of the screen for a moment. You can capture the problem and give it a try on your own. Many of you must have guessed by now that this problem is very similar to the one that was asked in JEE Advanced 2019. That problem and its discussion is also there in this channel. If not on this channel, then it is certainly there in my course 350 plus advanced illustrations. The important thing to realize in this question is that mass of this block is too large compared to mass of this ball. So when a ball hits the block, it transfers some momentum to the block, but because of large mass of the block, there won't be much change in the speed of the block. So in 1 or 2 hits, the speed of block is not going to change much. But obviously, if you consider a long period of time, then it will gain significant amount of speed. But in the question, it has been stated that for the time interval considered in the problem, we have to assume that speed of the block remains much smaller than speed of the ball. Okay? So I am assuming that speed of the ball at some instant is v and speed of the block is u. That means some collisions have already taken place. This is traveling at speed u and speed of the ball right now is v. It is going to make a hit, and just after the hit, speed of the block, well, it will be slightly larger than u, but I will write it as u only. In 1 or 2 collisions, speed is not going to change much. For this ball, let us assume that it is traveling back at speed v1. Because the collision is elastic, so coefficient of restitution is 1. So relative speed of approach and relative speed of separation are equal. If there is an observer over here, the observer sees that the ball is approaching it at a speed of v minus u before collision, and just after collision, the same observer will find that the ball is moving away from it at a relative speed of v1 plus u. So these two should be equal, relative speed of separation and relative speed of approach. That is, coefficient of restitution is 1, which means v1 is equal to v minus 2u. V minus 2u, right? Will I be very wrong if I take it as V only? Well, V minus 2u is very close to V, because in the language of the question V is always large compared to u. So, for some purposes, let us see for what purposes. For some purposes I can assume that V1 is same as V. For what purpose exactly? For purpose of calculating the time required for the ball to return back to make another hit. Suppose a hit has happened just now with the block. The ball is traveling at speed V1. It gets to the wall, suffers another collision, reverses back with same speed V1 and comes back to the block. In the time interval in which the block travels to the wall and is back, this block must have traveled a small distance, but only a small distance. Let us ignore that. In the time interval, the block travels this distance, the ball travels this distance. The block would have traveled only a small distance. We will ignore that. And we can safely assume that the time interval between two successive collisions is 2x by v, where x is this distance. If x is the instantaneous separation between the block and the ball, then this ball makes a hit, let us say at time t is equal to 0. The next time it is going to hit the block will be at this time. Block has not moved much. The ball will have to travel a distance of x plus x 2x at literally a constant speed of v. So, the time interval required between two successive collisions right now is this much. As x increases, this time interval will change. But at the instant this separation is x, this is the time interval between two collisions. And I can say that instantaneous frequency of collision, if I may say so, instantaneous frequency of collision is 1 by t, which is v by 2x. That means if you think about 2, 3, 4 collisions, then at this instant, number of collisions happening per second can be calculated like this, 1 upon t. Getting my point? Okay, the question asks a very different thing. I forgot the question actually. Determine the speed of the sphere at the instant the distance. Okay. We have to relate the speed of the ball and this separation x. Please notice that in every hit with the block, the speed of the ball decreases by 2u. Important. Whatever be the speed of the ball at an instant, it is v, after some time it is v1, after some time it is v2, whatever be the speed, if it makes a hit with the block, then change in speed of the ball will be 2u, where u is the instantaneous speed of the block. So, change in speed of the ball is 2u in a time interval of this much. In a span of this time, the speed of the ball changes by this amount. Can you see the logic? This is change in speed of the ball, delta v. Let me put a negative sign in fact. It is decrease in speed of the ball divided by the time required for this decrease. This is actually delta v by delta t, isn't it? This is delta v by delta t. Let me write it as dv by dt, where v represents the speed of the ball. Now, let me put it like this, dv by v, okay, minus this v, I can take it here, dv by v is equal to 2 goes away, u by x into dt. Okay, let me write it like this. Now, this looks a bit clumsy, but if you take note of a minor thing, it simplifies. In fact, it gives you the result. And that observation is that u is nothing but dx by dt. So, in place of u, if I write dx by dt, In place of u, I am writing dx by dt. dt will cancel out. Can you see that? It will become like this. So, dv by v is equal to minus dx by x. As simple as that. If you integrate on both sides, what do you get? Log of v is minus log of x plus a constant. I am doing indefinite integration. Let me write it as log of c. So bring this on this side. This is logarithm of v into x is logarithm of some constant c, which simply implies that vx is a constant. V into x is a constant. V into x. What is v? V is the speed of the ball. What is x? X is the separation of the ball from the wall. So, v into x is a constant. Oh my God. If v into x is a constant, this simply means, just a minute, this simply means initial velocity of the ball v naught into initial separation, initial value of x, that is L naught, will be same as final velocity of the ball v into final separation, that is 2L naught. So, this v becomes equal to v naught by 2. Can you see that? V into x is a constant under the assumptions given in the question. The change that is happening, the important thing to notice is the change that is happening. Change means change in the speed of the block, change in this distance. That is fairly slow, that is very slow. And for 2, 3, 4 collisions, we can always assume that x has not changed. It makes actually no difference to your calculation by assuming that x has remained same for 2 or 3 collisions. So, time interval between 2 successive collisions is this much. Inverse of that is frequency of collision. The second part of the question asks you to calculate the ratio of average force exerted by the sphere on the wall at L is equal to 2L naught compared to the initial average force. Well, the force depends on 2 things: the momentum transfer per collision and number of collisions happening per unit time. We have already calculated that frequency of collision is v by 2x. This frequency will remain same for block as well as wall. You can think about it yourself. For this wall, the frequency of collision, number of collisions happening per second, will be equal to v by 2x, where v is the instantaneous speed of the ball. And what is change in momentum of the ball in every collision it encounters with the wall, not the block, wall. It is very easy. For this wall, change in momentum of the ball in every collision will be 2 mv. So, transfer of momentum per collision is 2 mv and number of collisions happening per unit time is v by 2x. So, naturally the force, the average force you can say, will be this much that the wall will experience, and this will be equal to mv square by x. So, initially v is v naught and x is L naught. Finally, v is v naught by 2 and L is 2L naught. So, you have to give the ratio of these 2 things, the final force that the wall is experiencing divided by the initial force that it was experiencing.